said before, the title of my thesis is Assessing the Potential of Finite Element Modeling to Explore the Influence of Luthier Choices. Okay, now like this, everybody can hear me. Okay, so let's start. Violin making is deeply rooted in tradition. Millions of violins are created each year, and most of them came from a copy of a historical instrument. When we speak about instrument made by luthier, the process is largely handcraft. This process also involves several complexities. It is highly irreversible and wood varies a lot, even within the same tree. After selecting the wood, luthiers can mainly control the geometry, and today we still doesn't fully understand the parameter that cause the changing of the sound qualities. We don't even have take a standard for saying what actually it's really a good sound. And for trying to solve this question, we can explain by arriving in the experimental way, but that it's costly. We can provide evidence practice, but this is scarcely applied, and modeling tools that include all the material, the assembly, the interaction, and everything. It's very, very complex. So to understand how violin vibrates, we have these scenarios about many people arrive to the violin by trying to understand, some of them, how the musician arrive to the violin, how they play, another how the bow interact with the violin. Other scientists take into consideration the string, the impact directly in the bridge, another the instrument, myself, some other people in the environment, and another into the how the listener perceives the sound. But for understanding my part, that is the instrument, we have to be very carefully about understanding the geometry, the material, and the assembly. Okay, so the violin is composed of these elements that we have in the screen. Some people doesn't know that it has the bass bar, the sound post, and we have also the bridge that is not glued to the instrument. If we ensemble all these, we have a violin. When a string is bowed, it's under a stick slip motion, producing a periodic temporal signal. If we analyze this signal with an FFT, we obtain the string partials, which are the basis of the harmonic content, but the timbre of the instrument is not determined by the string alone. It also depends on how the violin and the bridge respond. It means that we have a system, couple of subsystems that interact and create different response on the instrument. The bridge mobility acts at the center, coupling the elements between the string and the corpus, and its frequency-dependent behavior filter and they redistribute the energy, and this is strongly influenced by the geometry, material properties, and the bridge and the corpus. To understand the violin through the finite element model, we can go for down to up, in the sense that we are including more and more parameters. We can first start by understanding how the material works and even a level of microstructure. We can understand how each part have a role in... C'est quoi?
Je voulais enlever le turn off volume, mais bon, tant pis.
Le quoi? Ah oui. Oui, ça marche. Okay. Okay. Also, we can go in the opposite direction by understanding how each part affects the complete behavior of the system, no? Okay. Now it doesn't work. Okay. Okay. First, I'm going to talk about how people have approached this problem by finite element. First, we have the work of Roberts, who started with plates. Also molding in 1988, Yu in 2010, and Go in 2015. But the problem is that actually we are not hearing a plate vibrating. We're hearing an instrument, and not at all do this first approach by modeling this complete body of a violin in 1989. The problem is that it's very simplified a level of geometry and properties, and also we have the approach of Bretos et al. Who link to create a correlation between the plates and the box. The problem is that the geometry we have here is very, very idealized. Now going to what can we call the new generation of finite element models, we have first Perez in 2013 who reverse engineering of Strauss violin, but the problem is that he doesn't have a stepwise verification, and I'm also not very sure about if we can for sure have a good accordance into a CT scan. But also Goff in 2015 shows a very beautiful model that show how the plates they adapt one to the other by including the ribs step by step. I mean, he put a rib with a low stiffness and then more and more stiffness until we see how the signature mode appear. Via in 2018 to 2024, he created a model-based ranking model, but the problem is that it was not based on experimental information. Torres and et al. Create this parametric violin that we have here that is adjusted to obtain the A0 by using resonators. And the main problem is that the geometry is very simplified. We have also in 2024 work that is stepwise from a finite element digital twin of a single violin corp, but they are not considering a full batch and they are suggesting to adapt the air in future works. So when we hear a violin, we put a force here that make the violin begin to sound. What actually we hear is the movement of all the assembly that has glue together and how it distributes the air around us. Actually, this way travel to our ear, and that is actually what we perceive as sound. But the problem here is that it's not very easy to understand what is the relative influence of each of these parameters in the behavior and how the makers could use these parameters to take decision. Could be this or could be this. It's not very easy to see how this work. So our goal was to create a finite element model for a batch of violins. This approach lets us to study the influence of the material properties separately, which cannot be raised on the reality. And it also allows us to evaluate uncertainties linked to the production of the specific batch. With this, we can predict the effect of parameter changing during the construction, especially showing how design on material choices modify the system response. Now, the outline, I will present experimental data in the first part. Then I'm going to explain how we reach to the different stages of construction, and then the influence of the vibration caused by the thickness variation, then the influence of the material properties in the modeling, and then the conclusion. Between 2016 and 2018, the Bilbao project was created to address a question that has been longer raised in the field of acoustic. Can decision made during construction be related to the vibration and sound in such way that we can predict it? Basically, they were trying to create a path into the mechanical properties to how the sound we perceive. To this end, 6 violins were made, their manufacture being exhaustively controlled and their only geometric variation being their thickness. This was done because the aim was to understand whether the mechanical properties of the instrument influence the acoustic properties related to the listener. The violins were numbered randomly and used for perceptive testings. The Bilbao collect a huge set of data experimental that they took in different stages during the construction. This gave me the opportunity of validate the model in 5 different stages. This is each measure they take in the analysis. This is the one of the process, another, and at the end, it's me who analyze this information. They create a geometry from CT scanner that allow to reproduce by CNC the top and the back plates without human error. This is important because having an stable geometry is something almost impossible when you do a violin by hand. They also do their best in the wood selection. What we can see in the screen is difficult to get wood from the same tree. That guarantee that the Bilbao do their best in trying to reduce this variability. And now I'm going to talk about the modeling of the CNC, which is my start point. To model a system in finite element model, we need to understand the inputs and the outputs. In our case, the inputs are the material properties and the geometry. At this stage, the geometry is fixed, so it means what are just going to vary is the material properties. So the variations are what actually cause impact in the modal shapes and the eigenfrequencies. The modal shape is the way the body is behaving in a certain frequency. The system solves the fundamental equation of structural dynamic, which is a very interesting equation because has in the interior the second law of Newton, our assumption that we have in damping, and also the Hooke law, and basically that's what these do. Okay, now talking about the wood, that is our first problem here. It's highly variable, it's heterogeneous, it's direction dependent, and it's very difficult to characterize. So for arriving to characterize it, we assume it like linear, elastic, homogeneous, and orthotropic. So it means that experimentally and simulation speaking, all the time we are just working with the overall values of the piece that we are analyzing on a determined moment. Okay. Wood is treated as an orthotropical material, meaning it has three different directions. One is the longitudinal, the other is the radial, and the other is the tangential. Tangential to the grow rings. You know, it's like circles here. This means that we can build this led us to describe the mechanical behavior with this constitutive matrix, which links strain into the stresses according to these three orientations that we will use in the modeling. A simple way to describe this is a strain vector is produced of the compilant matrix that has that leads in three Young modulus, three Poisson ratio, and threshold modulus. Okay. Now, the geometry that we are using is the actual geometry they use for creating the violins, and I'm able to mesh it without losing information about the surfaces or the volume, and I'm orienting in the way that the luthier normally do. The longitudinal is red, radial is the green, and the tangential is the blue. So now that we know that the geometry is very well known at this stage, we can talk about how to arise the problem of the wood properties. The first step is to run the model with parameters that we know from the literature, and we perform a sensitivity matrix. In that way, we see which parameter affect in which direction. The problem is that we have here a different behavior from the density to the stiffness. It means that we have a problem of global multiple local minimums. That means that we can have different configurations of parameters that give more or less the same value. So for that we need to fix the density, but it's more or less easy. We have the volume of the body, and we have the weight. So by understanding the density, we can estimate the influential parameters that are the parameters that cause more changing in the system. The other parameters that are not in this matrix, we don't put them because they are having impact of almost 0. For the routine described before, we start from the density related empirical laws. Then we run the model. We see how the eigenfrequencies and the eigenvector behave, and we constrain it by using a cost function. This cost function is gonna tell us if what we are having in eigenfrequency and in eigenvector actually has a concordance. The Mach number, model assurance criteria, is a robust tool that we can use for this procedure, and we create a matrix of agreement. It means that we compare mode 1 to mode 1, 2 with 2, and all of the different modes. If we have disturbation here, like we are losing coherence, it means that our function is going to say, this is not the path you have to follow. We have to have the most concordance between the eigenvector and the eigenvalues. When we have the convergence in the algorithm, we could say that the properties identifier are this one. No? Okay. By obtaining the mechanical properties of the wood and running the simulation to verify, we can see the match between the measure and the simulated modes. And we can see also that in all the cases, we are decreasing the error. So it means that for the 12 plates that we have for creating the 6 violins, we are having a good match in eigenfrequencies and also in eigenvalues. This work led us the opportunity to publish in Acta Acústica in 2025, and it's now time to see if the properties that we have calculated here have concordance in the next stages of construction. So now that we have this model, it's not just a matter of reviewing each part of the modeling to obtain consistent model. Doing this allows us to see if the properties that we have calculated are good enough. So in this second stage, we integrate the actual manual grading of the top and the backs. Each has different grading criteria. The backs tend to show very clear lines of the thickness, while the top have a less marked pattern. For the backs, I tried to directly reproduce the lines drawn by the luthier, but this method did not work very good for all the geometries. Instead, for the top, I developed an alternative method, and I created an adaptive grid, who actually deals with the problem that the photos are not orthotropic. I'm showing here you the best photo, but although the other photos are less orthotropic, so orthonormal. So at the end, we have to see what thickness each luthier reports in each part of the mesh, and in that way we retire the material from the backplate, and that is how I graduate them manually, virtually. As we can see, we have different thickness achieved using the same methodology, ranging from red, which is the thinnest, to blue, which is the thickest. We have 12 plates in total, but I'm going to show you 6 for reasons of space and because it's easier to see only the overall differences. So we can see that here in the medium is more or less 3.5 in almost all the plates, with certain rate points that the luthier didn't control, and the thin plates, they have more red zones, and the thick plates, they have some part that they are very thick. So using the same modeling idea proposed before, we can introduce these already graduated parts and see that what we obtain. As we can see, the model shape and the eigenfrequencies are congruent. This confirms that material that we calculated before remains valid, having an average error from 3 to 2.1%. This confirms the properties has been optimized. When we do this, two things at the same time, the geometry concordance and the material characterization, which is also a good way to do it. Now, let's talk about the modeling of the body, where the problem increases exponentially and makes the role of finite element modeling quite interesting. The complete body consists in the top plate with the base bar, the back plate, and the rib garland. The rib garland is consisted in the ribs that they are blended, the blocks that are here, and also the linings. At the end, we are doing also something that in the literature was not done before, is taking into consideration a tangential curvilinear orientation for the contour of the rib garland, and also we are oriented the blocks. This was not done by Gogh in 2015, also not by Torres, and Akar in 2024 also mislead this orientation. Now, knowing in advance that Dakar in 2024 proposed to include the air and having taken in the future by correctly orientation the ribs, which they ignore, we add a sphere of air. This sphere of air, it's a coupling between the air domain, where this is completely mesh, and this adaptative to the wavelength that we have inside. In that way, we can see that we have the solid mechanics, the pressure acoustics, and the multiphysics. It means that each time the mechanic solid move the air inside, it's gonna create a pressure that is actually how the violin works. As I told you before, it's basically a very complete model. At this point, an interesting question arises: what happens when we model an assembly violin without air and with air? Something changes. First of everything, we don't have A0. This nomenclature from A, it means that it's a mode that is representative for the air. B it means this mode is representative of the body movement, and we lose the mode dependent of the air. But we also have a bad coherence in the body mode. Here in this moment of defining the signature modes, they are more modes. Another is the CBR. It's a center bound rhomboid. I'm going to show you later. And also we have another family. It's B1 plus. Okay. At the corpus stage, a focus on damping is necessary. The damping is computed through a complex viscoelastic modulus associating the storage and loss modulus, and the damping through the viscoacoustic coupling. The plot compares experimental model damping values with numerical prediction for the same corpus based on the complex eigenfrequencies. We observe a clear difference at low frequencies where the model tends to underestimate damping. Therefore, the numerical damping seems simplified and does not capture the phenomenon such as joint losses or correctly aerostructural iteration. The agreement improvement at higher frequencies would suggest that the material damping assumptions are more valid in that range. The remaining discrepancy might indicate missing vibroacoustic coupling, which is not included in the stage of the model. It means that we need to understand more deeply what is actually happening. As we can see here, it's double, and this is coherent to the experiment. On the left, we can see a comparison between the simulated and experimental model frequencies for one corpus. The diagonal tries to show that the model reproduces most modes with reasonable accuracy. These remain scatter high sensitivity to wall properties, boundary condition, and geometry tolerance, especially for the B1 minus modes. On the right, we have a directly mobility analysis. This approach gives a very detailed frequency response and clearly shows how material orientation affect the bridge mobility. However, direct method simulations are computationally speaking costly. So this motivates the needs of perform something faster, because it takes 2 weeks of computation each curve just for coming from 0 to 600. So even having more is more costly. Okay. Here we have a compared measurements and simulated body using a model-based reconstruction approach, which is faster than the previous full direct analysis. At first glance, the agreement was reasonable in terms of resonant frequencies, but we still see clear discrepancies in the amplitude. This point probably issues in the model post-processing, most likely related to the mass normalization FRF reconstruction produces. Direct finite element analysis does produce better agreement, but is computationally expensive, as I said before. So the challenge at this stage is to improve. But we also have the question, why is this happening if we take out from COMSOL to improve? Now, let's talk about what happened when we complete the violin. Okay, the body of the violin behaves differently when the bridge and the sound post are added. That is when we can consider a complete body. It's even interesting how we can predict the performance quite accurately by ignoring parts such as the fingerboard, a string, or another accessory. This is because the no signature modes depend of at least these elements being present on the simulation. I pay a lot of attention in having a good details in both elements, and the material properties I'm using are related to the density and are usual values for these. We can see that the simulated modes, once we run the model, correspond to those measured experimentally. And we have here the complete family of signature modes. The A0, that is the mode of the air. We have here the measurements and the simulated. The CBR, the center rhomboid, center bound rhomboid. The B1 minus and the B1 plus. For the 6 violin, the overall error predicts second frequencies not superior to 5%. Okay, we have a functional and validated model that we can use it, but the fear we have to take into account is the variation that we could do in terms of violins. This slide presents the experimental protocol we used to quantify variability in violin mobility measurements. The objective was to determine how much uncertainty comes from the measurement process itself. We considered 2 cases: low intra-specimen variability, where conditions are kept constant, and high intra-specimen variability, where we deliberate introduce regluing effects, and then derive a total uncertainty envelope. We use 2 independent measure methods: a laser vibrometer that we have here, and a hammer with an accelerometer to compare these 2 measure methods. This campaign we perform in 2 violins and 2 isolated corpus structure. For each configuration, we carry out 3 averages and 3 full repetition, with sensor removal between each repetition. This allows us to identify which source contribute to the most mobility measurements uncertainty. And also we go in deeper. First we repeat measurements by removing and putting a gain sensor, but then we unglue and reglue violins. And for the repetition of the measurement, we have an error of 0.1, when also error in the deviation, the amplitude of 1.4 decibels. Then we perform 3 complete openings and regluing processes using traditional bone nerve glue. We were very careful into the proportions and repeat the mobility and each style. This in order to have the variability in just coming from the measurements, and then from things that we are not allowed to control, like the glue. Now, with the information that we know now, we can really understand how the thickness variation affect the the violins, and for this it's important to know the relation between the entrance and the input of the violin with using a FRF. By exciting the bridge it brings us the overall vibratory behavior. It means that what we measure here is more or less how the whole violin behave, and we reconstruct this by taking 150 modes to see what was happening outside. Now we are going to compare two same thickness violins by applying perturbation on the curve according to the calculated coefficients that we said before. We are going to take into consideration both. Okay, it's not easy to compare two violins just by seeing the curve. Some people could say, okay, they are similar. Some people could say, no, I don't find them so similar. So for doing this in a scientific way, we simply take the difference between the two curves, then we divide the difference by the normal scatter. We always see when we repeat some measurements on regularly the same violin, and the result of the division becomes in a p-value. If something comes down from the p-value, we could say that statistically speaking there is some significant difference in the violins that we are measuring. And in this case that we have same configuration in terms of we are talking about medium, but they are not exactly the same violin. We have also a peak here. And if we go through the high variability, we have the cloud here that we can see more or less how these behave in terms of high variability, and we see also the same differences. Some of them in the signature modes, this big peak around 1000 hertz, and the rest of the curve remains no big difference. So we can also this numerically, and the curves are different because it's a simulation, and we see that we lose the peak here in 1000 hertz, but we have some differences in the signature area, and also a big difference here. That means that our model is more sensible to the CBR mode. Taking out the zoom and showing to 3500 hertz, we can again make the same computation with the numerical part and see that we have more or less the same behavior. To summarize the comparison with uncertainty, we look at the main cases. First, two violins with a similar thickness on geometry. Experimentally, we see clear differences below 300 and around 700, but the overall signature modes remain stable with only one strong deviation in 1100. Numerically, the model reproduces difference between 370 hertz, 700 hertz, and slightly underestimate the higher frequencies. In the documents, we test the effect of changing top plates with different experiments, and we ship peaks below 1000 hertz, especially around 350 to 500, confirming that the soundboard thickness influences the signature modes, and above 2000 hertz, there is not clear different effect, meaning that other components are dominating there. Numerical results show similar trends, particularly around 400, 530, 650. Because mobility computation remain challenges, we propose for now a comparative analysis rather than absolute experimental numerical matching. But also we have the question about the properties of the modeling. Fully characterize the orthotropic behavior of the violin is difficult in practice because, as we said before, the geometry and it needs special tools and equipment. By contrast, density is very easily to measure accurately with simple tools. So the question is whether reliable density link relation can predict K-elastic moduli, such as the Young modulus. If the correlation are strong, luthiers and engineers can estimate material properties directly from the density. If not, more advanced approach like our model are interesting. And here we can see what happened when we put when we perform the simulations using the density based loss, and when we use the optimized wood properties, we see that even we say, okay, this is not a good concordance and this is a good concordance, but globally, even if we have a good concordance, all the times they improve. So it gives us the insight that the density based laws are not enough to characterize the material. And the same result with bridge mobilities, significant difference between 350 and 700. So we conclude that the density linked relations are a powerful first order predictor for a global trends and comparative studies. For instrument-specific prediction and fine spectral control, measure or update material properties remain necessary. Density link material properties relation reproducing nature mode frequencies typically with an error about 5%, similar to the natural variability. Yet some instruments, like the one we discussed before, deviate significantly from mean material trends. Density alone cannot capture the diversity of orthotropic stiffness and damping in the real tone wood. So, a full violin finite element workflow was developed for free plate and assembly corporea with string coupling and controlled batch of 6 violins. This has never done before. Nobody has ever analyzed 6 violins at the same time, and even less without the same geometry. High fidelity geometries and stepwise validation significantly improve prediction accuracy with error typicals between 3 and 5%. Model-based mobility reconstruction is promising, but currently we are still limited about it. We need to mainly do the damping assumption, and experimental determination variability determine realistic comparison threshold. So it's more or less what we talk about the differences in frequency and in decibels. Thickness variation clearly impacts signature modes below 1 kilohertz. So it means we have to be very careful in what happens in the signature modes. Density elastic relation are powerful prediction, but we're still having the problem of the 9 violin. So as future work, we propose a better approach for modal reconstruction, and we implement the rest of the body, the scroll, the string, the accessories, to see if the differences in the pressure level are also apparent, because our model has air. It's a good idea to continue understanding what is related to the air. And the perspective, we can use the validated model as a decision support tool before building new violins, to predict the effect of construction before carving, to test alternative base bar on some post strategies virtually, and propose geometry preset for a target spectral behavior. Using this information in this project, we can use them in collaboration with the luthiers and the scientists to make protocols that avoid errors we have that could appear in projects. And it's important to obtain a reduced order model to excite with an harmonic signal for the bow, and in that way we can use it to synthesize sound for perceptual test. So thank you very much for your attention, and that's it.
So thank you, Amaury. We just wait a few seconds for people to leave the room, and then we will start with the discussion phase.
Mm-hmm.